Thank you, and I would like by starting by thanking the organizer for inviting me to give a talk here. So I think this is a really nice workshop, so I'm having fun. The work I'm going to present is a spectral graph of random quantum channels, and it's a joint work with Ion Nekita and Marius Jung. So the outline of the talk will be the following. First, I will start with some motivation, if you are not yet too motivated. Then I will state our main result. I will mention some applications of it, and then the sketch of the proof. So let's go with the motivation, but before starting, let me recall the definition of quantum channel, or the equivalence definition. So a linear map is a quantum channel if it's completely positive trace-preserving map, or if there exists a family of operators that we usually call Krauss operators, that such that the map can be written in this way, and such that it's trace-preserving, that translates into this condition of the operators when the dimension of the set of operators is different, then the trace-preserving condition is not, the identity goes to the identity, but there is a correction factor. And then the other characterization of CPTP maps that I'm going to use is the Stinespring representation that says that there exists K and an isometry that goes from CD to the tensor product of Cn times Ck, such that the channel is just the action of the isometry, and after we apply the isometry, we trace the second part of the system. In fact, I'm going to use it instead with an isometry. I will usually enlarge this system so that I have a unitary. But OK, so what's my motivation? Where is coming from? So in 2007, Hastings proved the following result. So he took a set of unitary matrices drawn at random with respect to the Haar measure, and he considered the following channel with Krauss operators ui divided by a square root of k. So for this channel, first of all, it's clear that the identity is a fixed point because it's a unital channel, and then there is one eigenvalue 1 that is associated to the identity. Well, of course, this is always true for completely positive trace-preserving maps when the two spaces are the same, because we have a fixed point theorem, so we always have an eigenvalue 1. And the second eigenvalue, what he proves is that the absolute value of the second eigenvalue is upper bounded by 1 over square root of k asymptotically. So besides proving this, that it's only an upper bound on the absolute value, he took a different set of random quantum channels. Essentially it's the same, but instead of taking k independent unitaries, he takes k over 2 independent ones, and then the other k over 2, he considered the adjoint of these unitaries. So with this, then the operator Fn is Hermitian, and then it's easier to give a lower bound. Well, it's easier. It's still complicated, but one can derive a lower bound for the second eigenvalue. And for this case, he could prove that the modulus of the second eigenvalue, there is a modulus missing, sorry, it's converging to 2 times the square root of k minus n over k. So essentially 2 over square root of k when n is large. OK, but these channels are unitary channels. So their Krauss operators are unitaries, and they are unital, but they are not all the channels that we can consider. So why cannot we consider, first I'm going to keep on with the motivation So these channels, to the best of my knowledge, were first introduced by Hayden et al., and they proved that these channels were epsilon randomizing maps. That means that essentially almost every matrix goes close, epsilon close to the identity. Which is kind of the same result, but they are not totally analogous, so one cannot derive one from the other. Well, essentially the epsilon one, yes, but if one has an upper bound of the second eigenvalue, then you can derive that this map is epsilon randomizing, but not the other way around. So several applications of Hasting results, just to keep on with the motivation. So first, this channel is a quantum expander. Okay, so this is almost by the definition of quantum expander. So what is a quantum expander? So a quantum expander is something that has first eigenvalue equals 1. Every channel has first eigenvalue equals 1, but associated to the eigenstate, the identity. So it's usually a unital channel, and such that the second eigenvalue is lower, upper bounded away from 1. So it's essentially what he proved, right? But what is the intuition behind quantum expanders? So quantum expanders are just maps that whenever we apply it many times, well, not many, several times sequentially, they go fast to the identity. Well, the identity because it's the fixed point. If the fixed point is not the identity, it could be to another point, but we ask the condition that this point has high, so it's close to the identity, has high entropy.
So the convergence is with respect to how we understand convergence?
Well, in any norm, essentially. So, but convergence in norm to the identity. So if you have a difference between the first and the second eigenvalue, then everything gets mapped closer and closer to the identity after repeating the channel. Okay. Also, there is a relation between CPTP maps and one-dimensional translational invariant matrix product states. At the moment, I'm not going to say this relation. I will speak more about it. But what I'm interested in is in mentioning that then the existence of a gap in this completely trace-preserving maps translates into an exponential decay of correlations. That meaning that if we have one of these one-dimensional systems that is given by an MPS, I will talk further about this later, and we take two regions, A and B, that are L-sides separated, then the correlations between the operators acting on region A and B is decreasing with the distance of these two sets. Also, well, these channels are closely related to the first counterexample of the additivity of the maximum output entropy that Hasting gave. Essentially, it's this channel, but where the weights are also random. So it's instead of 1 over square root of k, there is 1 over square root of some pk's that are random. Okay. So then the question is, what happens if we have, instead of some unitary channel, a general channel, a random channel that is not, doesn't need to be unital? Can we bound the difference between the first and second eigenvalues? In particular, can we show that the fixed point is close to the identity, has large entropy? This is a question that Hasting posed in this paper, actually. And the question is, okay, if you want to do general random CPTP maps, how do you sample the cross operators? So in principle, you have to preserve this condition, and the easy way to preserve this condition is just using the Stinespring representation and sampling random hard unitary matrices. So the set of random channels that I'm going to consider is the channels from Mn to itself, such that I apply a unitary to my state tensor product with some initial state, and then I trace the part of the ancillary system. Okay, and then, of course, I will take the Haar measure, the only one that is invariant under the action of the group. But in general, why one would restrict only to this set of channels and not consider any set of channels where the dimension of the input and output spaces do not coincide. So I'm in particular interested in the growing ratio between d and n. So when d and n goes to infinity at a given ratio, sorry, lambda. Okay. So can we say something about these channels? Of course, now it's not a question about the eigenvalues because these are not the same dimensional. So it's a question about the singular values. Can we bound the difference between the first and second singular values? So this is a question that Hasting posed also in a paper in 2015, but it's not with this given ratio. It's for d, k, and n going to infinity at some particular ratio, because he's interested in proving some decaying of correlations. I will talk about this a bit later. Okay, so our main result. So what does it say? So essentially it says that for some particular values of k, when k is a bit big, then I can prove, or we can prove that if d over n, so if d and n goes to infinity with d and n at a given ratio, then we can bound the first singular value lower bound, we can upper bound the first singular value, and we can upper bound the second singular value. And when I say that we need k to be big, it's because somehow we want this bound to be smaller than the first singular value. Otherwise, we are not doing anything, right? So this constant that appears here and here is some universal constant that is not depending on n and d in particular, and it's upper bounded by 4. So let's go to the case lambda equals 1. So if I write my statement for lambda equals 1, what I have is this upper bound for the first singular value. I didn't copy the lower bound, which is here. So it will be 1 or 1 plus 1 over k minus 1 over k square root. So a bit bigger than 1 if lambda is bigger than k. If lambda is smaller than k, sorry. So of course, we know that the first singular value is always greater than 1 because we have actually an eigenvalue that is 1 in this case. And for the second singular value, this will say something if this is smaller than 1. So if C is upper bounded by 4, then I need k to go as 16 squared to say something. So it's not really a great bound, but at least it's a bound. So for k big but finite, we can prove the difference between eigenvalues. How? So using Bayes' theorem about the sum of the modulus of the eigenvalues is less or equal than the sum of the singular values, and I have upper bounds for the singular values for the first two, and I have that my first eigenvalue is 1 because we have a fixed point theorem. Okay, so then I have this estimate for the modulus of the second eigenvalue. And so whenever k is big enough and n&d goes to infinity, then I will have that my channel is with high probability gapped. So it has a gap between the first and the second eigenvalues. Okay, so yeah, this is what it says here. So in fact, I don't need n and d going to infinity. We can prove that we can get probabilistic estimates for fixed n and d. And again, this means that for k big enough and finite, we can give random channels of fixed n and d that will be up with some probability. It will not be going to 1 because everything is fixed, but it will be some non-zero probability. And it will be increasing as n and d goes to infinity. And actually, it's increasing quite fast, but OK. And the other thing is that having these estimates allows us to compute other gap for the other scalings. So when I have different nk and d going to infinity, then for some of these scalings, I will have that my channels are gapped. Of course, in the sense of the singular values, because the dimensions are different. OK, so what are the applications of this? So the first application is just the same as the set of random unital channels of Hastings. So these channels are quantum expanders. Again, they are quantum expanders because there is a difference between the first and second eigenvalues. And that means that whenever I apply the channel several times, it will converge fast. Well, how fast? Depending on the difference depending on the second eigenvalue, of the modulus of the second eigenvalue, which is how fast the part of the eigenvalues that is not the one is going to 0, how these eigenvectors are decreasing in norm. So now we don't have that the identity is the fixed point of this channel, but nevertheless we have that the entropy of the fixed point can be estimated, and it's close to the identity depending on k, but it's not getting closer and closer to the identity. So it's actually bounded away from the identity, but quite close. And whenever k is going to infinity, then this estimate is going to then the fixed point is going to the identity if we take k going to infinity. So why is that? Okay, it is clear, maybe I should have mentioned before this, that if k is large and n is fixed, then this is the simple ratio of this convergence, because I have an ancillary system really big, and then I'm evolving my state with an ancillary system of a big dimension, and then I'm tracing the ancillary system. What I'm going to get is just the identity, if the ancillary system is huge. So this is so k going to infinity is the easy case. That's why we are in principle interested in the k fixed case. Okay. So for the correlations of one-dimensional systems, as before, if I take, again, the matrix product states that I didn't introduce yet, and I look at the correlations of them, they are decaying exponentially with the distance. So it's exactly the same result, but then the set of matrix product states is more general. I will go to them in a moment. But these are just the cheap results that you get only by doing the same that Hastings has done. So the other relation about correlation of 1D systems that I'm not going to talk too much about is that in 2012, Brandau and Horodecki proved that that whenever we have exponential decay of correlations in a one-dimensional system, then this system has to fulfill an area law. And they give a bound in the area law depending on the length of correlation, of the parameters of the decay of correlation. So Hastings, this is the paper I mentioned before, has conjectured that this bound is optimal. That meaning that the bound on the entropy that they describe in terms of the correlation length is sharp. So for that, he proposed an example well, it's not an example, it's a proposal, because it's not yet proven to be an example of the sharpness, and a sketch of how the proof would go to prove that this is sharp. So in particular, he proved some bound on the entropy of these one-dimensional systems, and what is left to prove is how the correlations of these one-dimensional systems decay. And this is not easy in principle, and the first conjecture that he posed in this paper is a conjecture about a spectral graph of random quantum channels. And this random quantum channel, we can show that it's gapped. So somehow we solved the first kind of step in the unproven conjecture. Okay. Of course, there is still a lot to go, so it's not quite as straightforward. Okay. Okay, let's go now with random matrix product states. And I like to think about how did I arrive myself with this problem. So I was not in principle interested in computing the gap of random matrix, of quantum channels, sorry. I was interested in studying properties of random matrix product states. So for that, let me introduce what the set of random matrix product states is. So first, a matrix product state is just a description of a state. So in general, states have of n-partite d-dimensional system have d to the n parameters, right? But we can define matrix product states as the set of states that can be written as the trace of the product of matrices, such that these coefficients can be written as the trace of the product of matrices. So if these matrices have dimension dk minus 1 times dk, and this number is bounded, all the coefficients, then the total number of coefficients n is n, the maximum of these numbers, d squared. If d squared is small, comparable with d to the n, then this is not the whole set of states. But if we take this decay going as d to the n, then the set of matrix product states is exactly the same set, is the whole set of states. So if instead we take d a polynomial in n, then these are not the whole set of states, but nevertheless, these are the set of physically relevant states in one dimension at least. So this was proved by Hastings in a different paper. So it's the same year. But what he proved is that whenever we have a Hamiltonian with local interactions that is gapped, then the ground state can be approximated by matrix product states. So somehow these states are the ones that are the low energy eigenstate of the interesting Hamiltonians. Okay, so what happens if we look at first of all, the translational invariant case. So in principle, this, maybe I should explain a bit more. These matrices here are tensors. They depend on three indices. Well, they are matrices if we fix I1, but if we don't fix I1, they are tensors of three indices. So these two are the indices of the matrix whenever we fix I1, and this is the index of I1. So then I have a tensor that I represent by a box with three legs that are the indices of the tensor. And in principle, these matrices could be different depending on the position, depending on the system. But we are going to be interested today only in the translational invariant case, that is when these matrices are all the same. So they are the same for whenever I1 is equals I2, the matrix that appear here, well, in this product is the same as the matrix that appear in this product. So if we write the translational invariant case for open boundary conditions, which is this case whenever the matrices at the end are just rank 1 projectors, and the other matrices are all the same. So I can write the density operator of my matrix product states in this way. Okay. So in this case, we proved in 2013 that if one takes such a product state, such a matrix product state, and I take a random matrix product state, how do I take a random matrix product state in this setup? So the way to take a random matrix product state is motivated by thinking on this reduced in this density matrix as generated by a channel. So we can see R as the initial state of the system, and then apply the channel, this channel here, that has two tensors going out, one up and one down. So this channel is the one I call E here. So it's something that takes a matrix that is of dimension capital D and two matrices of dimension capital D times small d. So capital D is, sorry for the notation about capital D and small d, but it comes from the world of matrix product states. This capital D is the bond dimension of the matrix product states, and it has to be, it is related with how entangled can be these sites. So somehow this is related with the Smith rank. It's exactly how big the Smith rank of these states could be. And the small d is the physical dimension. So it's really the dimension of this spin of these systems. Okay, so what we are doing actually in this picture is taking a matrix that I'm gonna, or a channel that I'm gonna see as a unitary, acting on, in principle, something on dimension d, capital D, times something of dimension d small, but I will take this as a fixed state, and then I have the Stinespring representation of a channel. So somehow, what I have here is that in order to generate this matrix product state, I can generate this matrix product state sequentially by applying this evolution many times. And this is why this is a reasonable way of sampling these channels if we are thinking in these random matrix product states, because we can create a matrix product state sequentially. Okay, so the relation between these AIs and the matrix U is here. Well, it's just writing in a pictorial way what we have in the equation. So okay, then row n is exactly apply n times the channel to the matrix R, then multiply by the matrix L, trace the dimension D and the bond dimension, and we are left with the physical systems. And if we think of what we are doing, we have a channel whenever we trace. So if we trace in this map one of the physical systems, so for example here, if I trace this physical system, what I have is a map from MD to MD. So I recover the quantum channel that I defined before with dimensions D and D, capital D and capital D. So this is just by tracing this index here, then I have a map from this side to this side. Okay, that is defining just by tracing the physical system of the other channel, this big channel. So this is really the set of random channels that we were considering before. Okay, so what we could prove with this set of random channels is that in this setup, so whenever you have a 1D chain of n systems that is given by a matrix product state and with some boundary conditions, L and R, whenever you take these matrices at random, so you take the random channel, and whenever you take R and L at random, if we consider the reduced density matrices, density matrix of an L site, then the entropy of this reduced density matrix is close to maximal. So this meaning that somehow if in a big chain we look at the small part, then everything looks classical, or another way to see it is that it's maximally entangled with the rest. So this is so in this way we could recover a principle of maximum entropy whenever we sample in this set of matrix product states. Okay, but recall that this sampling in this set of matrix product states is just sampling in the set of ground state of local Hamiltonians with translational invariant interactions. So we are sampling in a set of physical states, and we can still recover a principle of minimum entropy. So this idea is not original of us. It was already done for non-translational invariant matrix product states by Oliveira and Garnerone and others. And also it was, the first result of this kind was just proven for the whole set of general states, which is just that if you take an state of some dimension, bipartite states, where the ancillary system is big enough, when you trace, you are left with the identity. So it's kind of the same principle, but with a more natural set of quantum states, more physically reasonable. Okay, so why do I care about this problem, or why do I come back with this problem now that it's solved? Because this is the open boundary conditions case, but another case of this problem is whenever I take the infinite chain. So if I take an infinite chain, the limit whenever I have infinite systems, then I have an infinite translational invariant random matrix product states. And if here I want to take the reduced density matrices of L systems, what I will do is contract all these physicalist indices, take the trace on all the ones over here and the ones over here in all but L of them. So what happens if I do that? So you can think of in the limit I will get a matrix at some point, and then I apply the channel, our random channel, many times, so I will get to the fixed point after probably not too many steps, because this channel is gapped in general. So what I will recover is that in the right part of what I haven't traced, I will have the fixed point of the map. So this is the fixed point of my random map. So this will be a random matrix that is the fixed point, and I don't know how it looks like. Okay, well, we know the entropy, or we know that it will be with high entropy, but we don't know exactly how it looks like. And in the left-hand side, what we have is the adjoint channel acting many times, and the adjoint channel has only one fixed point, which is the identity, so I will have the identity here whenever I trace. So my reduced density matrix over L sides will have this view, so this form. So why is well, this was a problem in the previous paper. We would have liked to do that, but we didn't know how to do it. And the point was that this lambda u, it depends on the channel. So I don't know how to take the moment of method or measure, compute the moments here, because this is depending on the channels itself. So now I know that lambda u is the fixed point, but I know it's the only fixed point, and I know that it's uniformly bounded in all the unitary matrices away from the second from the second largest eigenvalue in modulus. So instead of putting here lambda u, I can substitute the lambda u, but by some repetitions of f in the identity. And I will get an estimate uniform over u of how, well, with probability, but uniform in probability, of how these guys are near. So how much am I losing in this approximation? And then whenever I have the identity here, or well, I will have other actions of the channel and the identity, I can compute the moments. And then I can repeat the calculation that we already did in the previous paper. And then we have the same result as before, but for an infinite translational invariant random matrix product state. Okay. So let me sketch a bit the proof. So let me recall the result. We had the first singular value that was some quantity that appears also in the, no, sorry. There is no lower bound here. Maybe I should have copied. It's the case lambda equals 1, the one I copied. Sorry. Maybe I can go back. Yes. Okay, so I have, well, this maximum that I will talk about it later, but I have a quantity here that it's a lower bound of the first singular value, and it appears in the upper bound of the singular value, plus another quantity that appears in the second, in the bound of the second singular value, in the upper bound. And this is because of the way I'm computing the bounds on this singular value. And so I think it will be clear from the way of from the sketch of the proof. Sorry. Okay. Okay. So instead of working with the operator, what we are going to do is work with the super operator, with the seeing it as a linear map over vectors. So the singular values of these maps are exactly the same of the singular values of this operator. So I'm going to work with this map. So in principle, we know that the identity is not the fixed point, but somehow we expect the identity to be near the fixed point. So if one if one divides this operator in two, one that is the projector onto the identity and the other that is the orthogonal projector, then one should expect that this guy here captures almost all the first singular value, and that this other guy captures the rest, or gives a good bound in the second singular value. And this somehow is an idea that already PCR exploited in the unital case. So I will comment further about this in a bit. So first we bound the singular values of this matrix, and then this is a rank one, so computing the moments is easy, and we can get sharp estimates on the singular value of this guy, so this is easy to do. And then for the other part, and this converts to this quantity, which was one of the quantities that appear. And for the other part, okay, this is the same. For the other part, what I want is compute again the singular values of this, but with the projection onto the orthogonal of the identity. So Pisier gave another proof of the result by Hastings of the unitary channels that essentially goes in the next direction. He gave a norm inequality relating these guys for the case where the cross operators are unitaries and independent in terms of a norm of the Gaussian matrices. And besides independent Gaussian matrices, where there is many steps in between, that first is related with the Gaussian matrices, then is decoupling the Gaussian matrices. Afterwards, you have to bound this quantity. But essentially, what we have done is the same, but for the case where these cross operators are not unitaries, but are boxes of the unitary matrices, which are our cross operators. So we get exactly the same like lemma, but changing the cross operators by the other cross operators. So this 1 over k shouldn't be here. It's definitely the super operator without the 1 over k. Okay, so once we have this inequality, then take q equals 1, compute the average of the infinite norm by bounding in terms of this guy, and then bound the right-hand side of this guy for q equals 1, applying Chebyshev's inequality. Bound this guy, and then we will get some number extra, and then apply Chebyshev's inequality with different values of p. And this gives you this estimate. And actually, it gives you estimates for d and n finite. So that's why we can recover the d and n finite estimates also. So once we have this, we just have to apply the well-known inequalities between the singular values as a sum of an operator that is sum of two operators. So for example, this one and the other one, the first singular value is the sum of the two, is less or equal than the sum of the two, nothing too complicated. That's why the bounds are not so good, and that's all. Essentially, we are done. And these are the references I've been talking about. So the paper is not yet in the archive, but hopefully will be soonish. Thank you.